Hi everybody, I wanted to go over this portion of the unit with you asynchronously. A lot of this is background information or previous knowledge having to do with atomic structure. So I'm going to cover this objective 1.5 in this manner, and we can address any questions that you might have in class as well. So for this particular lesson, you'll be able to tell how atoms and molecules can be identified by their electron distribution and energy. And this do now question, this is meant to be done in person, but I'm going to ask for your answers next time I see you. Okay, so things you need to be able to do for a College Board. You must be able to represent the electron configuration of an element or ions of an element using the Aufbau principle. You will not need to memorize these names. You just need to know how to apply the rules. You need to know that an atom is composed of negatively charged electrons and a positively charged nucleus containing protons and neutrons. And you need to know that Coulomb's law is used to calculate the force between two charged particles. So the Coulomb's law is the activity that you did in class. You will not need to mathematically calculate Coulomb's law, just understand it theoretically. And the second bullet is, that's Regents information. When we talk about electrons, that's what we're going to focus on here. I'm assuming that you know the atomic number gives you your number of protons. And then if you take your mass number for a particular isotope minus your atomic number, you get your number of neutrons. So when you're dealing with atoms and ions, electrons can be thought of as being in shells or energy levels. In Regents chemistry, we call them principal energy levels. That's perfectly fine. And subshells or sublevels. For some reason, College Board calls them subshells. I call them sublevels. Most people do. And this can all be described in the electron configuration. Any electrons that are not on the outermost principal energy level are called core electrons, and outer electrons are called valence electrons. The electron configuration is explained by quantum mechanics, way beyond the scope of this course, and it's shown on the periodic table, and this is so important. Your periodic table does not give you any information about electron configurations. You need to be able to use the layout of the periodic table to get the electron configurations for an element. A vocabulary word that we're actually going to look at later in the week is ionization energy. You will need to know this information. You know what, I'm just going to skip this for now because we'll talk about that when we get to PES. So things you should already know how to do is be able to describe subatomic particles in terms of mass, location, and charge. So if we just lay these out real quick, protons have a mass of 1 AMU. They are in the nucleus. They have a +1 charge. Neutrons also have a mass of 1 AMU, also in the nucleus. Oh, why can't I write? Have no charge. You see what time it is. Electrons, we ignore the mass. They're approximately 1,800 times smaller than the mass of a proton or a neutron. They're in your electron cloud. They're in orbitals, and they have that -1 charge each. By the end of this lesson, you will have some familiarity with constructing electron configurations using sublevels and orbitals, describe Heisenberg's uncertainty principle, describe the shape of orbitals, which you don't really need to know for the test, and use Aufbau and Hund's rules. So the planetary model of the atom, the Bohr model, has electrons traveling in these fixed pathways, and that's really not the case. But through a whole bunch of math that you take higher level chemistry courses in college, there's more letters than numbers, and they change, languages of the alphabet. You get Greek letters in there. They describe the behavior of electrons as being particle and wavelength. It's called duality. And that leads to the quantum mechanical model, or the wave mechanical model of the atom that we have today, that sometimes electrons behave as particles, sometimes they behave as waves. What we do know is that electrons have specific energy, but they do not follow specific paths. They are in regions of probable electron location, which are called orbitals. Okay, so an orbital is a region of probable electron location. You can calculate the energy of an electron, but you cannot also know its exact location at that given moment. But based on the amount of energy it possesses, you can tell relatively how close to the nucleus it is. The scientists chose to study, the hydrogen electron, which they labeled the 1s electron, and they found that it's moving rapidly, but just not in circles. And then this Heisenberg uncertainty principle, there we are. It's impossible to know both the location of an electron and its velocity or speed at the same time. It's more probable to find electrons closer to the nucleus and in lower energy locations. And you don't have to worry about that last part. The 1s orbital is the radius of a sphere that encloses 90% of the total electron probability. You don't have to know that. Let's see what else I can do here. Come on, go back. I love the lag on this. These calculations continued. So they started with this 1s electron, and they took it from there, and they studied every element they possibly could. And they figured out these configurations for these electrons based on their probable locations. So we're going to be putting together these electron configurations based on the principal energy level the electron is in, the sublevel the electron is in, based on where it falls on the periodic table, S, P, D, or F, and then a superscript will tell you how many electrons are present within that sublevel. This next couple slides show you shapes of orbitals. You don't have to worry about memorizing these shapes. The S is a spherical shape. P is a pair of lobes that can exist on an x-axis, a y-axis, or a z-axis. Right? Z-axis makes three-dimensional, so you could have y, x, or z. D orbitals are weird shapes. F orbitals, they don't even really know a lot about them at this point. There's just another diagram of the p orbitals. You can see x, y, and z popped up there. Oh my gosh. These d orbitals, they're all over the place, so you don't have to worry about their shapes. Okay, super duper duper important here is the blocks where the elements are found on the periodic table. Okay, the blocks that are pictured here in blue. So helium, is kind of an outlier over here on the right-hand side because it's a noble gas, but helium is an S block element. So these first two groups, group 1 and group 2, your alkali metals, your alkali earth metals, are your S block elements. Then you jump all the way to the other side of the periodic table and you get these P block elements, okay, which means that if you have an element that falls within that green region, its valence electrons are located in a P sublevel of that particular principal energy level. Your transition metals, which are these transition metals, are this block here is the D block. And then the F block, you won't have to do configurations for those elements. We really don't ever deal with them in this class. What you need to notice here is the patterns based on the row numbers. What you need to be concerned of, though, is when you are in this 4s region. So this element right here is calcium that I just outlined in red. That's calcium in the 4s2, second position, 4s2. When you jump over to the next element, which I think is scandium, you're in the D block. But if you look at the number for the D block, it starts with 3. It doesn't start with 4. The reason for that is the first place where you see a D sublevel is the third PEL, not the fourth PEL. So when you are writing configurations and you're passing through that D block, you have to say 3D when you're in that first D row, not 4D. And I will go through some examples with you. Okay, so all we're going to look at here is I'm going to pull up the AP periodic table. Can't do that. Where's still recording? Let me try to screen share. My bad. I can't do both. fancy. Okay, so I'm gonna have to go back and use this periodic table. Okay, so we're gonna look at fluorine. Oh, this is gonna be fun for me to try to remember where all these things are. Okay, fluorine, where's my hard copy? Okay, it's late. All right, I know where fluorine and carbon are, so that's easy. I'm gonna throw my computer out the window. Okay, so here's fluorine. So we want to give the row and the block that it's in, okay? So since it's in the second row in the P block, it's a 2P element. Now what position is it in within that P block? It's in the 5th position. So if you were writing the electron configuration for fluorine, the very last thing that you would write for fluorine is 2, second row, P block, 5th position. Okay, so that's what it would come up with. The next one that was on that list was carbon. Carbon is right here. Okay, so carbon, it is in the, again, second row, P block, 2nd position. So that would be the last thing that you would write for carbon's configuration. Who was next? Manganese, sodium, and phosphorus. I don't want to keep going back and forth. Manganese, sodium, phosphorus. Okay, manganese is here. It's a transition metal. Okay, so what position is it in? It's in the, we know it's a D block element because it's in those transition regions. It's in the 5th position of the D block, and it's actually 3D. So even though manganese falls in the 4th row, it's in the 3D block. Next up we have sodium. Sodium is here. Oh, that's a bad color. So here's sodium. So sodium is in the 3s1 position. So the last thing you would write for sodium's configuration is 3s1. The last element example we're looking at is phosphorus, which falls here. So that would be in the 3rd row, P block, 3rd position. Oh no, there we go. Now, what's also important to note here is if you were doing an element like tin, so where does tin fall? Tin falls right here. Okay, so yes, it's in a P block, and it's in the 5th row, and it's in the 2nd position. So even though, yes, you had to like pass by these 4D elements to get to tin, like you're still in the 5P row. That slide is marked up. Okay, so the big thing, this Heisenberg uncertainty principle, just know that you can't predict the exact location of an electron, and then can you identify the number and sublevel of an element's valence electrons. So that's just where it is on the table. Can you pick out the row, that sort of thing, and the block that it's in. So what we're going to do now is build up electron configurations. So this section here at the bottom shows you that the order that they go in. So you can see as you progress through the elements, 1s2, 2s2, 2p6, 3s2, 3p6, that puts us at argon. Those are the first 18 elements that we've covered. How do I know I've gotten up to 18? If I look at these superscript numbers and I add them together, 2, 4, 10, 12, 18, that's 18 total electrons. So anytime you're like trying to keep count of like how many electrons am I dealing with, if you add all those superscripts up, that needs to add up to the atomic number, which tells you the position that you're at. Now we start with our next row. Our fourth row is potassium and calcium. So potassium would be 4s1, calcium would be 4s2, and then the next element is scandium. Your next element, scandium, we're passing into that D block. We're starting to get into the transition metals. So you have to say 3D1, not 4D. Okay, you have to drop back. But we're building in terms of energy. The 3D block electrons have more energy than the 4s electrons do. But the 4s electrons are considered valence electrons in that case because they are in the highest number PEL. And we will get into that in more detail. Okay, so this is showing you how to write an actual full electron configuration. Once we've established where the element is that we're talking about, we can kind of go back to the beginning and put together its whole configuration. So the red dot on the left here is where beryllium is located. So beryllium is in the second row in the S block, in the second position of the S block. So we know that the last part of its configuration is 2s2. So that takes care of that portion. Now we have to talk about what happened before that. Well, the electrons that are also present in the first PEL for beryllium are the two 1s electrons. So it would be 1s2, 2s2 as shown there. The other element that's blocked off in red here is sulfur. So sulfur, look at its position. It's in the third row in the P block in the fourth position. So it would end with 3p4. So if we go back to the beginning, start at the very beginning of the periodic table and just start counting through your blocks. 1s2, that takes care of hydrogen and helium. 2s2 takes care of lithium and beryllium. 2p6, that takes us through boron, carbon, nitrogen, oxygen, fluorine, and neon. I did that by heart. Okay, so there's our 2p6. Then our 3s2, that's sodium and magnesium. And now we jump over to our 3p, and since it's in the fourth position, it would be 3p4. It's all a pattern. You follow the pattern, okay? The biggest thing you have to remember is SPD, and then F for those really large elements, which you'll never get to. There's another picture of this one. What I would do if I were you is get a PDF copy of, or if you have a hard copy, use it. If you don't have a hard copy and you have a PDF copy, mark it up with these blocks to help you out. My cat is bothering me. Okay, you'll notice that the sequence skips around. The 4s is in front of the 3d. Yeah, that's fine. 4f has higher energies than some of the 5s. That's fine. This diagram shows you in order of energy how they fill. So you can actually see the overlap here. When you get to these larger elements, the 4s sublevel has slightly less energy than the 3D sublevel, and then it would be 4p and 5s and 4d. Now, if you just go in order of the periodic table, you will not have a problem. Like, you don't have to memorize, like, oh my gosh, 4s and then 3d and then 4p. Read the periodic table. Okay, there's no confusion if you just read it. You're like, this is all confusion. I get it. Now this is an orbital diagram which shows you like the placement of the electrons in these sublevels and orbitals. So here's the thing with an orbital diagram. An orbital itself, one orbital can hold a max of 2 electrons with opposite spins. So these electrons are spinning as they're circulating the nucleus. It would be like the worst carnival ride ever. And you can see the up arrow and the down arrow in these little boxes show you that. What you should remember, when you're talking about your blocks, so here's your sublevels, S, P, D, and F. The S sublevel has 1 orbital, and that could hold its maximum of 2 electrons. The P sublevel has 3 orbitals that can each hold 2 electrons, so that's a total of 6. There's your 6 positions in the P block. Here are your 2 positions in the S block. The D sublevel has 5 orbitals that can each hold 2 electrons, So if you look at your transition metals, that D block, there are 10 positions in it. And then your F block has 7 orbitals, so they're increasing by odd numbers here, each with a total of 2 electrons possible. So that's 14. And those F block elements that are separate at the bottom, there's 14 positions there. Okay, so let's look at carbon for a second. So carbon's configuration is 1s2, 2s2, 2p2. Okay, there are 2 electrons in the first PEL. There are a total of 4 electrons in the second PEL. 2 of them are in the 2s, 2 of them are in the 2p. If you were to draw an orbital diagram for carbon, I drew one line under the 1s because the s sublevel has 1 orbital. Here's the 2 electrons spinning in opposite directions. I put one line under 2s because there's 1 orbital. There are 2 electrons, they're spinning in opposite directions. Now, the p sublevel has 3 orbitals that can each hold 2 electrons, but the orbital diagram for this region goes like this. Those 2 electrons do not occupy the same orbital. That's Hund's rule. And again, if you want to call it by name to honor the dead guy, whatever, cool, good for you. You don't have to, but you need to know if you have to draw an orbital diagram or fill one in or pick the correct one in like a multiple choice question. Look, the Hund's rule states the lowest energy configuration is one having the maximum number of unpaired electrons allowed by Pauli principle and a particular set of degenerate means same energy orbitals. They should have parallel spins. So this little thing in English here, put 1 up arrow in each box before any box gets 2. Okay, think of it like the public transportation rule, especially in the era of social distancing. You're not going to sit next to anybody unless you have to. Okay, electrons are both negatively charged. If they have equal energy, they're trying to space out as much as possible. Okay, so they're not going to sit next to each other unless they have to. The next element after carbon, which is nitrogen, it would be 2p3. That next electron would go in the empty space in this orbital. Then when you got to the next element, which is oxygen, which is 2p4, now you'd have to start doubling up. Okay, you don't sit next to somebody unless you have to. Oh, how many unpaired electrons does nitrogen have? So let's look at nitrogen. Nitrogen's configuration is 1s2, 2s2, 2p3. So here's your 1s2, here's your 2s2, here's your 2p3. How many unpaired electrons does it have? 3 unpaired electrons. You could get a question like that in a multiple choice without the orbital diagram being given to you. It just might, you have to know how to do it. How many unpaired electrons does carbon have? If you can hear my computer right now, it sounds like it's taking off. 1s2, 2s2, 2p2. 1s2, 2s2, 2p2. It has 2 unpaired electrons. The last thing I have to go over here are valence electrons. Valence electrons in the outermost principal energy level. So it might not be the last thing that you write, especially in a larger element where you're starting that 4s, 3d kind of configuration. But it will definitely be the electrons that nitrogen has a total of 5 valence electrons. There's 5 total electrons in the second PEL. Phosphorus, which is just below it on the periodic table, also has 5 valence electrons. And this, that you learned in Regents chemistry, the elements in the same group have the same number of valence electrons. The transition metals, your D block elements, there's some variations in there, but your group 1 and group 2, your alkali metals, your alkaline earth metals, they all have 1 or they all have 2. And then your P block elements will either have 13, 14, 15, 14, 3, 4, 5, I can't count, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, yeah, that's 6 total. So you could have up to 8 valence electrons total. So things you need to be able to do, you need to be able to write electron configurations with for various, come on, for various elements. Again, you don't need to memorize the names of the rules, just know how to follow them. You need to be able to construct electron configurations using those sublevels, the 1s2, 2s2, describe Heisenberg uncertainty principle. You do not need to know how the shapes of these orbitals. And then know how to use the Aufbau and Hund's rule. Aufbau principle is you're going to go in order of increasing energy, and Hund's rule is you don't sit next to somebody unless you have to. You don't partner up electrons unless you have to. The next little part has to do with ions and noble gases shortcut, and I will go over that with you